So, okay, guys, thanks for joining. So, last day, I think last session, we have been discussing about the controllers. Then, yeah, mostly the controllers, right? Yeah. So, last session, I also planned for the path planner, but we didn't get enough time for that. So, today, we will be first starting with the path planners. And then, if we get time, we will be like seeing like how to work with the RQT plugin. I will give an intro of that. So and then maybe tomorrow we can discuss further. Okay. Okay. So I think we can start today's topic, that is ROS Path Planner. Okay. So like before starting with the topic, I need to give an intro, like the how I mean why we are learning this topic, and what are the advantages that you will get if you learn this topic, and what is the importance basically. Okay. Okay, so we can start from that. Okay. um, so in order to start with the path planner, I just want to start with the navigation stack. Okay. Yes, I hope you are familiar with the ROS navigation stack. We have discussed a lot about the navigation stack. We talked about the um, diagram, this diagram. I hope you remember the navigation stack diagram, which is basically the navigation stack is basically having a single node called move base, and we are actually configuring this node for working with autonomous navigation. Okay. And you also know the move base is not a single node. I mean, it's a single node, but the capability of move base is that it's like a node which can load multiple plugins. Okay. So it's a node that can able to load multiple plugins. For example, the move base can load plugins for global planner, then it can load local planner, then global cost map, local cost map, recovery behavior. Okay, so these all are the plugins that it can load. Which node? The move base. Okay, the move base can load these plugins. And I think we talked about the plugins, right? The plugin lib we have talked about. So the plugins are like a runtime software kind of thing. Like imagine your program is running and you can add some capability to the running software by adding plugins. Okay, so like that, it's kind of a dynamic kind of addition. Okay, for example, in Moobase we have the global planner and local planner. All the things we can replace with our own plugins. Okay, so there are some existing plugins available already with ROS. For example, if you just search for global planner ROS, that itself a package in ROS. When you install ROS, you will get this package, and it is having some inbuilt global planner. Okay, like A star algorithm, Dijkstra algorithm. So there are different global planner. I think you know what is a global planner, right? The global planner is simply like it can plan a path from the starting point to the goal position. Okay, it should be the shortest path. Okay, and we can also optimize that route. Okay, so based on the different algorithm, like the nature of the path planning can change. Okay, so this is one of the default package available in ROS called Global Planner, which is having some inbuilt path planner plugins. Okay, so like that, there are some default local planner available. For example, DWA local planner, which is one of the inbuilt local planner available, meaning it's already there in ROS. Okay, so you don't need to install it separately. I mean, it's already there. Okay. By the way, if you don't have any idea about the global and local planner, maybe I can give you an intro now, and then we can proceed. Okay. So basically what's happening in the navigation stack is that we can give the goal position. Okay. And the goal position will be going to the move base. Okay. And the move base is passing that goal position to the global planner plugin. Okay. And the global planner, it's actually planning a path from the current position of the robot to the goal position that is given. Okay. And which is the reference that global planner use? The map. Okay, here you can see we are feeding the navigation stack with the map. Okay, so it is planning, the global planner is planning a path from starting to goal position in the global course map. Okay, global course map. Global course map means we have the saved map, right? We have the saved map, like yeah, maybe I can show this. This is the saved map. Okay, this is a saved map, and this saved map is actually we have to publish, and the move base will be subscribing to it, and the global course map will be subscribing to this map topic and adding some extra layers into it. Okay, so the global planner can do the path planning from A to B. And what is local planner doing? Local planner doing is like, after getting the global plan from A to B, the local planner is trying to execute a segment of that. Okay, a segment of that, and so the function of local planner is, it is actually creating the linear and angular velocity in order to execute this plan. Okay, maybe I can take the PowerPoint and explain. So there is a question from Tejas, like, what is the significance of course map? So I think I have explained that. So course map is actually adding some extra layers into it. Maybe I can explain this after showing the global planner and local planner illustration. Okay, and yeah, so there are one more question from Rohan. Maybe I can take that after discussing this. Okay, so so we have the global planner. Okay, and the input of this global planner is the goal position. Okay, we have the goal position, and the global planner is having the course map, that is a global course map, and the global planner can give you a path. Okay, the path can be like, maybe we can imagine like this. Imagine this is the path actually generated by the global planner. Okay, so for example, this is start, and this is the goal. Okay, so this is the output of the global planner. Okay, and what the local planner does is that the local planner takes this path, okay, and try to execute each segment of this global planner. Okay, and try to execute means like the robot is here, right? So the local planner is trying to execute this segment, means it will try to go from start to this, up to this maybe. Okay, up to this position. Okay, so how it is going? It is actually creating the linear and angular velocity to the robot to move from here to here. Okay, so the local planner is the main part of the navigation stack, which is generating what? Command velocity, or the twist message, or the linear and angular velocity. Okay, so The global planner is using the global cost map. Local planner is actually using the local cost map. So if you have doubts in the importance of cost map, maybe obviously like we can discuss with an example. Okay. After that, we can come back to the planner. So let me start the turtle board simulation. Just a second. So I'm just starting the turtle board simulation, and then after that I will start the navigation. Okay, so it is actually starting. Yes. So this is a simulation of the turtleboard turtleboard 3 burger. Okay, so I'm starting the navigation. I think I can start the navigation without it. Just a second. Okay, I think it's working. Okay. So if you have confusion about that local cost map and global cost map, I can explain. Okay. Just a second. Okay. Yes, we have the setup right now, and we have the navigation stack here. Okay, and we have global cost map and local cost map. So how the navigation stack or the move base working is that I think I have shown you like how to build the map using slam and all, right? And after that we are running the move base or the navigation stack to able to move from A to B. Okay, so in order to run the navigation stack, we need a saved map. Okay, that is built using a slam algorithm. It can be a gmapping or hectoslam or anything. Okay, and we need a node called map server, which is actually there in ROS. Map server simply publishes the saved map as a ROS topic called map. Okay, simply. And also in order to work with navigation stack, we need like the TF, odometry, then the controller, then the laser scan, all these things we need. Okay, so currently if you take the simulation, you can able to see it is having the laser scan. Okay, it is having the map. Okay, and I think all the stuff required for working with the navigation stack. So in order to explain it, I think if you take the RQT graph, okay, so you will get an understanding. So RQT graph, it will take some time. Okay, so you can see here the move base is the node that we have talking about, and one of the input is the map. Okay, so who is publishing the map? Map server. Okay, there is a package called map server, and inside that there is a node called map server. Okay, and that is actually publishing the saved map into a topic. Okay, and which is publishing which is subscribing by move base. Okay, move base, you can see here this is a move base. So this is happening. And what about others? Like if you check move base is there, then the TF is there, then command velocity from move base to gazebo. Then I can switch to nodes and topics, so that will be very clear. You can see here move base map server publishing a topic called map, which is subscribing by move base. Then what is the input to the move base? Goal. Okay, so that is actually seeing here. Okay, and what are the other inputs to the move base? The laser scan is there, right? So where is the laser scan? That's what I'm looking for. Yeah, you can see here we are running the simulation, right? So gazebo is publishing the scan, which is going to move base, and it's also going to AMCL. Okay, and the command velocity is the output from the move base. You can see here it is going to the gazebo. Okay, and also the odom is one input to the move base. Okay, and in parallel with the move base, we need to run the AMCL node, which is actually showing here. It is for localization. It can detect the current position pose of the robot. Okay, so you got an idea, right? So this is a move based node, and it is having this much of input, and it is publishing some topics like command velocity, and inside that you can find local cost map, global cost map, global planner, local planner, all this stuff. Okay, you can see here local cost map, then local planner, global planner, global cost map, all the stuff inside it. It's actually plugins. So coming back to the point, let me show you the RVs. So here on the left side you can see here, if we disable global map, local map, okay, so what is the thing that you can able to see is simply the map. Okay, so here you can see there is a visualization of the map topic. Okay, so this is the map topic on the left side. Okay, so this thing is actually displaying the raw map topic. Okay, I'm just enabling global cost map. What is the difference that you can see? Any difference? Like I'm just toggling with global cost map and local cost map. So what is the add-on that this plugin is adding to the raw map? This is the raw map, and this is the global cost map. So you can obviously see the difference. Like the global cost map is taking the raw map and then adding some layers into it, right? So what may be the reason for adding these layers? So we have the raw map here, and we are adding some layers into it. What may be the reason why we need to add some separate layers on the existing map? Any idea? Maybe you can comment. What may be the reason why we need to add some extra stuff into it? Like yeah, so you can see here, right? There are some extra stuff added. What can be the reason? I think someone is typing. So you can think why, like from this diagram we have seen the map server is publishing map and it's going to the global cost map. Okay, and global cost map is what is creating this thing. Okay, this is actually the global cost map. You can see now it's very clear, right? I mean, without the raw map, if you simply visualize the global cost map, what is the main thing? Maybe I can explain. So if you just check the raw map and the global cost map, the global cost map is adding some extra layer into the raw map. Okay, some extra layer you can see here, like the black color that you are seeing in the raw map is actually obstacles. So global cost map is adding an extra layer into the already, into the obstacles that is already in the map. So what may be the reason why we need to add an extra layer? It is actually for the protection, right? Like if you create an extra layer around, extra obstacle layer, it's actually an obstacle layer. If you add yeah, so I think Rohan actually mentioned obstacle to avoid safe path. Yes, so it's actually for avoiding the obstacle prior to the actual prior to hitting the actual obstacle. Like we can detect the obstacle before it's actually hitting to the actual obstacle, because you can see here there is an layer already here, okay, obstacle layer. So it can detect, okay, robot can detect the obstacle before it's reaching to the actual obstacle. Okay, so that is actually, I mean, adding a safety to the robot navigation, right? For example, if you're driving a car, if there is a layer in which we can find the obstacle, and that layer is not a real obstacle, but it's like an inflated layer. Okay, so we can detect the obstacle before we hit the actual obstacle. So that is the purpose of the global cost map. Okay, and what will be the local cost map? The local cost map is actually a segment of the global cost map. So if I'm visualizing the local cost map, you can see here the local cost map is this much. Maybe I can disable the global cost map and real map. So you can see here it's actually a segment of the global cost map, and the local cost map can able to is mainly for working along with the local planner. Okay, there is global planner and local planner. So local planner is actually taking this local cost map, a segment of the global cost map. Okay, so there is a question why there is no overlap between global and local cost map. So these things are is actually overlapping. So these local and global cost map actually doing as a separate layer. Okay, so these are actually layers actually. Okay, but when we visualize it, we can see it a single map. Okay, but all these are separate layers. Okay, so the global cost map is the entire map with the inflated obstacles. Okay, inflation layer, it's specifically called inflation layer. Local cost map is actually a segment of the global cost map, which is having again some inflated layer, and also it is mainly for detecting dynamic obstacles and all. Okay, it can the local planner can able to detect the dynamic obstacles. Okay, so this is the main part, that is the global cost map and local cost map. Okay, I hope that is clear. And there is another question, how global cost map is taking laser scan and point cloud message. So I think the global cost map and local cost map, maybe it's actually clear here. If you check the diagram, the input to the global cost map and local cost map is actually the sensor source. Okay, so it can subscribe the global cost map plugin, and local cost map plugin can take these things as input. Okay, it's already there. Okay, so we don't need to do anything. Okay, if the Moobase is subscribing to the laser scan, then it is going to the global cost map. Okay, global and local cost map. Okay, so I think we talked about global and local cost map. Now we are coming back to the point, that is planners. Okay, so there is a question, but local cost map is already subscribing, so why global? Yeah, so the thing is that both layers, okay, both global and local cost map need the laser scan. So if you can see, this is a segment, that is the local cost map, but here also the global cost map also can update its map based on the laser scan. Okay, so actually the updation of the map is not only happening in the local cost map, but it's also required by the global cost map. Okay, both are actually required, but in the local cost map it is, taking an segment of the global cost map, and then the local planner is working based on this segment. It's not taking the entire global cost map for the planning. Okay, so when the global planner plans a path, it is also taking care of this laser scan for detecting obstacles and all. Okay, so so the question is there a scan matching going on between local and global? It's actually directly taking this. There is no scan matching happening. I mean, these two from this diagram, you can find both are independent. The global course map and local course map are independent. They are taking this laser scan and then they are doing the processing separately. Okay, there is no like scan matching between these two. It's taking the same input and processing in separate section. Like global course map is processing in the entire row map, but the local course map is only processing a segment of the global course map. Okay. Okay, so the question, another question is, can you put any object over in the gazebo so that we can check? Yes, yes, yes. So like the mapping, like if you for example, if you put an object here, yeah, just a second. If you put an object here, it will be immediately marking as the obstacle in the local course map. Okay, and the local course map and the local planner can immediately I mean change its route. Like there is an obstacle, for example, if I'm giving an obstacle here, I mean goal position here, okay, I think just a second. Yeah, I changed the planner. Okay, yeah, that I can correct it. Yeah, so what I'm trying to say is that when we put the obstacle on the local course map, it is actually updating the local course map. And also maybe you can check here, it's also updating the global course map. So like the local course map is actually a segment of the global course map, and it is actually I mean updating the global course map as well. Okay, so you can see here this is the global course map, and the global course map is having that obstacle, and if you check the local course map, it is also having obstacle. Okay, so instead of taking the all map, it is actually considering these sections. Okay, yes, so maybe yeah, maybe I can come to the point. So yeah, so this is how the global and local course map actually helping the planners to avoid the path. I mean, if there is an obstacle. Okay, so what I'm trying to show you is that yeah, so this global planner that we are going to discuss, global and local planner that we are going to discuss, is actually doing that in the global course map and local course map. Okay, and you can see here the input of the global planner is the goal position, and the output of the global planner will be a path. Okay, a path like from A to B. So you can see here the internal nav message path. So this is the ROS message type of that global plan. So if you just search for nav messages path, you can find a ROS message. Okay, ROS message type. So this is the type of the global plan. Okay, so that will be internal. We will not get the plan, I think. It will be going internally, and where will it go? It is going to the local planner. Okay, so the input to the local planner will be this path. Okay, and there are two more inputs. One is the odometry, okay, to the local planner, which is of type nav message odometry, and the local course map. Okay, the output from the local planner will be command velocity. Okay, so the local planner is actually responsible for generating the command velocity which will be moving the robot. Okay, okay, so before showing the planner again, I just want to change some parameters because I have changed to some custom planner, so that's why it's not working. Just a second, I think it's in the param or in the launch file, I guess. Movebase.launch. Just a second, let me swap into the okay, the global planner. Okay, let me just comment. Okay, fine. Let me start the simulation again to show the planner. Okay, the simulation is up. Now the navigation stack, launching of Movebase, and you can find the robot is coming, and let me just check whether it is planning properly. Yeah, now it's planning properly. Yeah, so now what I'm trying to show you is that I just want to show you the global plan and local plan, so you will get a clarity. Okay, so you can give the goal position to the Movebase in two ways. Okay, you can either like give the goal position from ROS from using this button 2D nav goal, or you can like publish this topic. Okay, there is a topic that you need to publish. For example, if you just check the topic list, I think the symbol goal. Okay, Movebase symbol goal. ROS topic info. See, it is publishing by ROS. So this topic is what we need to publish. Okay, so maybe I can just show you that I'm simply doing echo of this topic and I'm giving a goal position. So you can see this is the goal actually we have sent. Okay, from ROS. Okay, so you can see the position, goal position and orientation, and with respect to the map frame. So we are actually saying the robot to go to this position with respect to the map frame. Okay, where is the map frame? Map frame is actually the fixed frame here. You can see, okay, the fixed frame. And if you check the RQT, RQT TF tree, you can see the TF tree, TF RQT. Okay, let me check. Okay, visualization TF tree. You can see the map TF map to ODOM, which is actually publishing by the AMCL, okay, the localization node, so which is actually giving the map to ODOM. So if you are confused with map to ODOM, actually I can explain. The map to ODOM actually gives an estimate like where is the robot in the map with respect to map. I mean, where is the robot in the map. For example, you can see here the robot position with respect to the map is here, right? The current position. And if you check in simulation also, it is matching, right? So the AMCL node is responsible for that. Okay, AMCL node can give you the robot pose with respect to the map. Okay, the map is here, so it can localize the position of the robot like the GPS. using GPS you can localize it on the Google map, right? So similar to that, using AMCL it can localize with respect to this local map. Okay, and ODOM to base footprint is actually computing by the driver, okay, the controller basically. Then base footprint, all this from the URDF. So this is the TF3 actually currently now. Okay, so I just want to show you the global planner and local planner first. So if I'm giving a goal position using ROS, you can see a black line, okay, black line, and also there is a red line, and there is also a yellow line. Okay, so you can see closely, like you can watch. Maybe I can give a goal position here and you can watch closely. There is a black line, then a red line, and there is a yellow line as well. Okay, maybe I can increase the yeah, just a second. I can increase the size actually. Alpha. Yeah, this is actually good. So instead of that, instead of the root, we can actually use like the frames. So maybe this is somewhat confusing. Arrows is also confusing. Maybe the line is good. Line style. Okay, this will be good. You can see it is having a black and yellow, and also there is a red. So what happening is that these black and red is responsible for the global plan. Currently I think I'm a bit confused because there is two global planner is running, it seems. That I need to check. Basically the black corresponding to the global plan, okay, the global plan, and the yellow corresponding to the local plan. So you can easily find it out. Maybe I can just disable the local cost map for more visibility. So now the yellow is not very visible. See, so yellow is the local plan and the black is a global plan. So you can find it out, like the global plan is giving the path from the start to the goal, okay, and the local plan is trying to follow that global plan, okay, but it's not the exact it's actually a segment of the global plan, but it's not the exact, okay, but it's trying to follow it's like a reference, not the exact path, okay, but it depends on the kind of path planner that we are using. Like for some path planners, we can do like once the global planner draws a line or a path from A to B, the local planner will be exactly following the global plan. So that kind of planner is also there, okay, but the current planner that we are using does not do that. It's actually using that as a reference and mostly is trying to follow the global plan, okay. So Rohan, there is a question. So I think the red line is limited till the local planner window. You can see by giving goal outside, but the thing is that even if we give the goal position outside the local plan, even red is also limited. So you can see here. So I think it may be because of the visibility, it seems. Let me just check. uh, it may be, but I think, see, but it should be like I don't know, it may be because of the current setting, but ideally what happening is that it should plan a path from start to end. Okay. And uh, the uh, local planner is actually a segment. So I need to check it, Rohan, again, like what should be. Yeah, ideally when we check, both are actually I mean visualizing only up to the local cost map, but it should be like complete. The global planner will be complete, but local planner will be a section. Okay, it may be because of some settings or something. I need to check that. Okay. So the topic today is like how to create this global cost map and local cost map. I mean, if you want to create your own planner, how to do that? Okay, so there are some existing planners like standard shortest path algorithm like A star, Dijkstra algorithms are already there. But if you want to create a planner by yourself, how can we do that? Okay, and what is the importance? Like there are some good planners already available. So why do you want to create your own planner? So that's an important question. So the answer is that the planner behavior, it's not fixed. uh, like last time I mentioned, right, like this for this planner, if you just check, the global planner and local planner as not very I mean, it's not in very sync. I mean, it's trying to execute like the global planner, but there are some differences. Okay, so this is one behavior. Okay, but if you use some other planner like SBPL and DWB, I think I have shown you the MIR robot, right? Maybe I can also try to show you so you will get the difference. So based on the planners that we are using, the movement of the robot will be also different. Okay, in case of a, a warehouse robot. Okay, warehouse robot, you have seen the warehouse robots, right? Maybe I can take uh, AGVs, right? AGV. uh, so the problem with the AGVs are, maybe I can take, yeah. So you can consider these AGVs. This AGV should be moving in a certain way. There is a certain way assigned to this, but it can't move like the turtle board that we have seen. If it is moving, then I mean, it can, I mean, it's not a proper way in the warehouse, inside the warehouse, right? Because it should be keeping a certain path. So in that kind of situation, we have to write a controller and we have to write a planner, which can obey a certain path. Okay, so and there is another kind of thing like zigzag planner for agriculture. I can show you one thing. um yeah, so in agriculture robotics, if you check, let me check if there is any some video or some images. Wait, yeah, I think maybe I can take some Google images. Let me check if there is any. Yeah, this will be okay. And yeah, this is also okay, I think. Yeah, if you check this, uh, you can check, there is a, it's mentioning about the global planner for the, you can see here the title of this paper: modified A star algorithm for efficient coverage path planning in Tetris inspired self-configured robot with integrated laser scanner. So just read this: modified A-star algorithm for efficient coverage. Okay, so there are some applications that we need to modify the existing planner in order to create maximum coverage. Okay, like a zigzag kind of movement you can see here. So this robot should follow this movement, this kind of movement. But if you plan using some other planner, we will not get this kind of zigzag movements. Okay, so we can decide the movement or the trajectory or the path, how we have to create a path from the goal position and to starting position and the goal position. Okay, so the power of the planner is that we can decide in which path the robot has to move or in which way it has to move. Okay, so if you want to for example, if you want to move through this maze or something, it's not a maze, this is the map, and if you want to move like this, we may need to create a planner. Okay, also we need to create some controller as well. Okay, so you can find like in some agriculture purpose, ROS agriculture, it's a spin-off from ROS for agriculture application. So there are some planners like green ice area planner you can find here. These are actually for creating the plants for the agriculture field. So from this image you can easily find. See, maybe I can also share these links. Just a second, we can have a look. So this is what I'm talking about, guys. So if you want different kinds of plants for different application, we can use different planners. Okay, so we can simply replace the global plan and local plan, and we can create this kind of movements. Okay, so I hope you got an idea. If you have any doubts regarding the advantage or like the use case of planner, let me know. Like if you have any doubts why we need to create a new planner, anyway, like we have some existing planner, so why we need some new planner. So this actually this repository is from Green Sea, which is a company working on lawn mowers. I think Green Sea, I'm familiar with this lawn mowers. Yeah, so they have open sourced their planner in order to do this self-driving lawn mowers. Yeah, so this kind of application, we can use the existing planners from go from A to B, but it will not be as perfect like this. So you can see from the video itself, it's clearly covering all the areas. So this is Green Sea, and there is another company, I think Synth Robotics. They are also into Synth Robotics. They are also into lawn mowers. Yeah. So I hope you got the clarity, like why we need to create our own plugins. Basically, it is for different behavior, for creating different behaviors. I'm simply sharing these links. Maybe you can have a look later. Okay. And fields covered too. Yeah, these are interesting. Okay, so let me just close this, and coming back to our actual topic, let me close all this stuff. Okay, so coming back to the topic, guys, the planners. Before that, I just want to show you this. Navigation stack move base. Yeah, ROS move base. Let me take this. Yes, so let me share these links with you. So this page that I am currently scrolling, this is the documentation of MoveBase. MoveBase means the navigation stack. Okay. So if you just scroll down, you can find the input and output, like the topics that is subscribing by MoveBase, publishing by MoveBase, and various parameters of MoveBase. You can simply see here. There are two questions, I think. Is there any, from Kalpesh, is there any way to finalize the controller and planner? For example, which controller with a specific planner? Okay. So, okay, let me think. The controllers actually, I think, these two have to work in a I mean, these two having important role actually. The planner is just giving the path, okay, and the local planner is what actually executing this, and the controller is what executing the movement. Executing movement means the controller is actually subscribing the command velocity, and it is driving the motors, or it is actually creating the command to the motors. So sometime we may need to fine-tune the controllers. For example, like turning the robot, rotating the robot, we may need to fine-tune the differential drive controller. The differential drive controller, if you are working with the differential drive robot, we may need to do some kind of fine-tuning. So mostly, like if you are doing with some prototyping application, I think you can simply take the differential drive controller and whatever the planners you like, you can take it. But in industrial scenarios, I think you may need to do some kind of fine-tuning, okay, especially for smoothening the motions, okay, or you may have to rewrite some the existing controllers to achieve that kind of motion. Okay, so we will get the command velocity, and based on that, how to drive the robot. So that is what the controller is doing, right? So maybe I can also like share some controllers that is using in the industry. Okay, so maybe we can directly use that and check it. So I think we need to do some iteration to make sure these controllers and the planners are working well. Okay, there is no direct, I will say, like equation like for this controller, for this planner we can use this. I think that is not the case. Whatever the controllers, whatever the planner, we need to first iterate it. Like we can put the planner and then we can put the controller and then see how it works. Okay, if there is any modification required, we have to change the controller or planner. Okay, so that is my comment. Maybe I can also share some insight about the different controllers that is using in the industry. Okay, AGVs. Most of the controllers are like custom controllers, so it can do the job without. It's not a general purpose controller. Okay, okay, yes. So the next question is from Tejas. If you want to make a path planner controller which should have zigzag movement, so obviously the planner is having the zigzag movement. So you can take this diagram easily. Like the planner is creating the path, and the controller is receiving the input from the planner. The global planner is what mostly the zigzag movement is, and the local planner is what it's executing it. Okay, so we have to create the global planner and also the local planner. Okay, mostly we have to focus on the local planner because that is actually creating the command velocity in order to execute by the controller. Okay, so the zigzag is generating by the global planner, and the execution of the zigzag is doing by the local planner, and the execution of the movement of the robot is doing by base controller. Okay, so these three needs some kind of adjustment. So the zigzag is only by the global planner. The high level, I mean the zigzag movement, no? So I think you have seen the diagram, right, from the paper. That high level zigzag movement is actually creating the path, actually creating by the global planner. Then local planner doesn't aware of anything. It's actually having the input from the global planner, which is a zigzag movement, and the local planner is trying to execute each sections of the global planner. Okay, so the controller may not require to move like zigzag. I mean, we can implement that, but mostly I will say the best approach is that we have to follow this kind of thing, like global planner, local planner, and the controller. We can do maybe without the move base as well. That is another thing. Like we can totally ignore move base and we can simply like run using the controller. That is also there. But I am currently talking about the move base context, in the move base context. Okay, so in the move base context, global planner is what giving the zigzag movement, zigzag path, and this zigzag path is executed by local planner, and it is obeying by the controller executing. Okay, yes, so that is from Tejas. From Hari, there is another question. Do path planners always show shortest path? Suppose we need to follow circular trajectories. Yeah, so that's what Hari I mentioned. The path planners, I mean, it's not for only shortest path. It can be anything. I mean, the word itself, we can say path planning, right? So in general, we can say like in general application, the robot has to go to the goal position, right? So obviously we need to path the shortest path from A to B, right? But in some case, for example, in agriculture scenario, I think we already seen. Just a second. That's actually a good question. So maybe I can show you the singular case zigzag. Let me take, yeah. So in this case, yeah, this case. It's not very clear. Okay. Let me take that PDF again. So in this case, imagine this is the starting point and this is the ending point. Okay. So if you consider the shortest path, then this zigzag movement is not the shortest path, right? So, but the thing is, the path planner is not doing the shortest path. It is actually creating a zigzag movement. Okay, so that's what Hari, the question is. It may not be the shortest path, but in a general sense, we will say like it should go to the goal position, and the best approach is like taking the shortest path, right? But it may not be it should not be the case always. We can define it. So that's why we are trying to learn how to write a path planner to define the behavior of the robot. Okay, yes. So like follow a circular trajectory is possible. Yeah, it is possible. Yeah. Another question from Rohan. Could you please share the modified A-star algorithm for efficient coverage path planning? So Rohan, I think we have to first start with the basic one, and then maybe I can show you that. Like all these are like IEEE papers. Okay, So maybe we can go through the code maybe after discussing the basic. Maybe we can, let me see if we will get time or not. Okay, so we can see currently the thing is that in this chapter we are not discussing about the path planning algorithm, but discussing about how to write a path planner. We are actually discussing about the infrastructure, like what are the things that you require to write a path planner in ROS. Okay, but if you are discussing about the path planners, generally it's again a big topic. You got it right. So we are talking about like what are the packages or what are the things you need to create a path planner. Okay, then it's your logic, it's your algorithm to fill in. Okay, we are talking about the template of the path planner. Okay, yes. So if you get time, maybe not today, maybe tomorrow we can discuss that. Okay. Okay. Then another question: if this movement is fixed in zigzag manner, then why do we need to plan the path? We can set a path. Yeah. So there are places that we can already set a path. Okay, we can already set a path, but imagine this scenario. Just a second. Yeah. So in this map, maybe we can decide in which path the robot should go. Okay. Oh, just a second. They just needs a code. Maybe I can share the PDF. I think there is a GitHub link on it. Just a second. Yeah, I have shared the PDF. Tejas. Maybe you will get the link. Okay. So coming back to the point, the global planner may not be an intelligent planner, which is like doing the plan when we give a goal position. It can be a fixed plan as well. What the global planner does is that it gives a global plan. That's it. Okay. If you want to create a fixed plan, that is also possible. For example, in this case, we can do in two ways. If you decide that, okay, there is a fixed map, I just want to drive the robot through this fixed path. Okay, that is also possible. Okay, so you can write a planner, global planner, and when it gets some inputs or something, one got position, it will be outputting this plan. Okay, and this plan will be going to the local planner. Okay, so that is also possible. It may not be like a starting to goal thing. It can be also a fixed plan, and that is up to us. That's what I'm mentioning. There is no equation for it. The path planner can be anything. For example, if you load the path planner can create a circular trajectory. Okay, and the robot should be always going through the circle. It can be a path planner. Okay, path planner, the word itself, you can create your own path. There is no equation for it. It's in your hand, something like that. Okay, so I think you got the clarity, right? Okay. So coming back to the topic again. Yeah, so we have been talking about the move base. So if you simply search on this page, okay, you can see the parameters. Okay, parameters. You can see here. I hope you can see here. So in the parameters of move base, you can see base global planner, base local planner. Okay, so if you set the name of the planner that we are using, then the move base will be taking that planner. So that's why I changed the name. I think you maybe observe that, like in the launch file or something, when I have take this launch file and change the base local planner as the DWA local planner. So here is the move base node. Inside that I am changing the parameter called base local planner to DWA local planner. This one, this is already available. Okay, this is already available. And if you are not setting the base local planner or global planner, you can see here, if you are not setting the global planner, by default it will be navfn/navfn ROS. It's again a global planner. Okay, and if you are not setting the local planner, it will be the trajectory planner ROS. Okay, which is again a default local planner. Okay, so what we are trying to do is that we are creating a planner package. The planner is basically a plugin. Okay, I am coming back to that. And we are replacing the global planner and local planner name. We are first seeing the global planner. I mean the demonstration is only for the global planner. Okay, and local planner I can show you the template. Okay, so the global planner we will be seeing an example. Okay, and it's a template. Okay, it's a template, and then you can simply change this name of the global plan, and then MoveBase will be taking your planner for the navigation. Okay, so I think you got an idea, right? Like the MoveBase is a node which is having parameters, and one of the parameters is the global planner and another parameter is local planner, and we have to change this name like to your planner, so it will be taking the your planner. Got it? Okay, so if you simply search for ROS global planner, you will get the direct tutorial of this. You can see I can share the two links. Just a second. This is for the global planner, and this local planner is also there. Okay, this is for the local planner. So both tutorials are available in ROS Wiki, but when you approach it, you will have some confusion. So that's what I am trying to solve today. Okay, so I'm directly jumping into the local planner. The global planner. So let me just show you a package, a template package. Okay, I'm planning to just demonstrate that package to you. It's called maybe Relaxed A Star is one package. And is there any other package? A Star Planner. Yeah, this is also, maybe I can share the link first. There are multiple plugins available, planners available for a reference. So ROS A Star, no, not this, A Star Planner. Okay, yeah, maybe we can take this as an example. Okay, so just a second. I can share this link. Okay, now we can just see how a planner package looks like. Okay, so this is a very basic planner. A Star, the same thing available in ROS, but we can see how the planner looks like. Okay, so initially I mentioned that a planner is a plugin. Okay, a controller is a plugin. Okay, and the nodelet is also like a plugin, and we have seen a lot of plugin kind of packages. So the same architecture or same method is there for the planner because it's a plugin. So if you just check the package.xml, you can find here the important dependency for creating a planner. Plugin lib, okay, is an important one, and ROS-CPP. Okay, then the nav core. This is another dependency for creating the plugin because it's all related to the navigation stack, right? Okay, and if you just closely check in the export tag, you can see we have to export the plugin name. Okay, so that XML file is here. You can see here in the XML, you can see the name, the class name, then yeah, this is the class, class type, and this is the base class. So basically there is a class, the library called navcore. So if you simply search for navcore, which is the API for creating this navcore. Okay, so this is the package which is having class called base global planner, base local planner, and recovery behavior. Okay, we are using this package in order to create our own planners. Okay, so this navcore is having what? Base global planner. Okay, so if you want to create your own planner, what you have to do is you have to inherit from the base global planner. Okay, so this is a base class, and this is the class name, and this is a class that we have written. The same thing. A star planner is the class name, and this is the namespace. Okay, so that is about the XML and package.xml. And in the CMake, you can see it's a plugin, right? So we have to compile as a build as a library. So this is how we are building as a library. You can see here, add library. Okay, add library. You can use add library for building as a library. So that is only the difference. Okay, so I think you got an understanding, like for a plugin package, or especially the planner package, the very important dependency is navcore, then the plugin lib, ROS-CPP, standard message. If you want to use any other, ROS-PI is not required, but other dependencies are very much required. Okay, so there is a question: what is the difference between base local planner and DWA local planner? So base local planner is actually the base class. Okay, base class. It's actually we are you can see it here. So that is the base global planner is a base local planner. That means that is the base class, and using this base class, they are creating the base local planner, DWA planner. Everything is mentioned. You can see here, base local planner is providing the DWA approach for the local planner. Okay, so that difference is here. So the base local planner is actually the base class or the interface. Maybe I can demonstrate that. So here, this is navcore. Okay, and from the navcore, inside the navcore, we have which class? Base local planner. Base local planner, right? Yeah, base local planner. Yeah, so that is actually the interface, like this. And using the maybe the naming may be the confusion. So I got the understanding. Yeah, so using, maybe I can use the same naming. Yeah, okay, and using this class, we have to create the your own local planner. Okay, from navcore, there is a base local planner class. We have to inherit and you have to create your own planner. Okay, so this base local planner is actually another planner based on this base class. You can see here. Maybe I can share the link. So that is the difference, Rohan. I hope you got an understanding. This is a base class for global planner. This is a base class for the local planner. And if you take the global planner package, which is actually a global planner implementation of this base class, similar for the local planner. So the question is from Tejas, base local planner and DWA both are implementing DWA algorithm. So you can see the difference here. See, the base local planner provide implementation of DWA approach and trajectory rollout approach. But DWA local planner is modular DWA implementation with a lot of cleaner and easier interface to understand for holonomic robot than base locals DWA. So the difference is here. Okay, I hope that is clear. I think the difference is here. And commonly using local planners are TEB local planner, okay, which is an improved method. Okay, so I think there is a clear distinction between all these things here. So the base class, then the name of the planner, okay, then the recovery behavior, everything is in the nav code. Okay, so yeah, so that is the structure of this package. Then you can see the code. There is nothing more fancy. For creating your own global planner, as I mentioned, we have to inherit from the base global planner class. Okay, so if you follow this, you can easily create your own planner. Like you can simply see here, there is a star.h, a-star.cpp. a-star.h is having the class declaration. a-star planner.cpp is having the class definition. So in the declaration, you can easily find the class called a-star planner, that is the path planner class, and which is in a namespace called a-star plugin. Okay, so that's why you have seen, if you take the plugin.xml, you can see a-star plugin / a-star planner. This is a namespace. Okay, so simply check, it is inheriting from the global planner. Okay, and what you have to do is simply you have to override these two functions. Override simply means if you inherit from this class, you will get some functions, okay, to override. Override means to define. So it's simple actually. From the function itself, you can find initialize and make plan. Okay, so when you load this plugin, it will call the initialize function, and when it when the global planner is receiving the goal, it will call the make plan. Okay, so the initialization is actually like the initialization for planning the global planner. No, for planning the global plan, it should require the cost map, global cost map. So that is what the initialize function does. And the make plan, this is where we have to implement our planner. Okay, so the make plan can give you the start and goal. Okay, and you can return with the plan. Okay, so the question is from Tejas that initialize is from base global planner, and we are trying to update that method with some new values. Yes, so these functions, I'm not sure you heard about virtual functions. So when you inherit from the base global planner, you will get some functions. Okay, so these two functions, these are the two important functions we need to define. Okay, all other things are specific to this planner. This is not mandatory, this is all up to us. Okay, if there is nothing, you should declare these two functions for sure. Okay, and you have to define it. So in the star.cpp you can find in the initialize function definition is here, then make plan function is here. So inside the make plan you have to put your planner algorithm. It can be an A star, it can be a fixed path, whatever you like you can put, and then that plan should be passed to this plan. Okay, it should be in a form of geometry post stamped. A plan is actually a vector. Vector means like it's a group of poses. Okay, that is actually the plan. So you have to you can apply your planning algorithm, and finally you will create a plan. Okay, and plan will be returning to the, basically it is returning to the local planner. Okay, so that is what actually happening. I'm not explaining the code because the code is specific to the A star, but we don't need to learn the code. We need to learn the framework or the structure, how we can do that. So in the initialize function, you can see whenever we load this plugin now, we will get this cost map. Cost map means the global cost map. Okay, so from this cost map value, we will get the size x, y, then we can iterate to this cost map. You will get the xy, it's like an image. Okay, so you will get the values of the cost map. So all these things we can initialize in this function, and in the make plan you can apply your planner algorithm. Okay, you will get the start position, goal position, and then you can apply your a star logic. Okay, then it will be like converting into the plan, and then it will be returning. So if I define it very simply, there is three things you have to understand: inherit, declare, and define. Okay, that is only the thing you have to do. Okay, I can also show you one more plugin structure, and after that we can conclude. Okay, I can also just include these plugins in Turtleboard, and I can show you how it is loading. Okay, so relaxed A star, you can see the plugin.xml, RA star planner ROS, and if you check the source code, same structure. You can take the ROS.h, RA star ROS.h. It is inheriting from base global planner, and then overriding function initialize make plan, and then you can see it is defining initialize function and also make plan. Okay, so just use your logic to understand this flow. Okay, no need to like by heart all this step, because this is specific for the RA star. Okay, but if you know how to create this plugin architecture or plugin framework, you can apply your own logic. Okay, so this is how we can build a planner. Okay, and I can simply show you like maybe in the initialization, maybe I can add some printing statement like 1. Okay, rows 1, hello RA star. I'm simply like adding a 1 here, and also in the make plan, which is actually like a while loop. Okay, it will be constantly I mean executing. I'm also like just a second. Where is that? Yeah, make plan. Rest plan. Okay, so I'm simply added some print statement just to show you, and then I am building it. Catkin workspace, then catkin make. Okay, seems like it's building. Okay, I just build the relaxed A star, and then I'm just going to Turtleboard repository, I mean workspace, sorry. Just going to the navigation package, just going to the parameter, just going to the launch file, move base launch file, and changing the global planner to what? To RA star plan. Okay, so local planner is DWA, RA global planner is this. Okay, so we have the package ready. Make sure you have sourced that workspace and just change the name. So now what happened? Now the move base will be looking for this planner and it will be loading. So let's see how it goes. So I am starting the simulation, and unfortunately the RA star planner will not work as I expected. Like there are some bugs in the code, but it will be loading properly. So that's what I am trying to show you. It is loading by move base. So I'm starting the navigation, and you can see the messages. You can see here RA star planner initialized hello RA star. You can see here, right? So that means the RA star planner initialized successfully, and you can see the message. And now I am giving a goal position. Okay, so now if I am giving the goal position, it will be triggering which function? Make plan. Okay, but it will not create a path, unfortunately, but you can see the messages. Here you can see hello RA star plan. So it's saying not valid start or goal, some error, but you can see hello RA star plan. You got an idea, right? Yes. So that's what I just want to show you guys. It's actually loading, and it is running or printing this statement RA star plan. So this make plan will be continuously calling when we give a goal position. Okay, I hope you got an idea about the global planner. Okay, maybe tomorrow we can see the local planner, I mean the structure, and then we can go to the RVs plugin. Okay, so now it's a time for questions. Let me know if you have any questions. Let me know. After that we can conclude. Question, guys. Any questions? We have actually discussed about the global planner and the structure, actually, like how we can create a package and then add that into the navigation stack. It's very easy to add your plugin to navigation stack. Simply give the parameter name. Any questions? Is that clear, guys? Okay, I hope you got my point. So yes, thanks everyone, thanks for attending. So tomorrow we will be seeing with the local planner, I mean just an idea, and then we will be switching to the RVs and RQT. Okay, bye everyone. Thanks for attending. Bye.